So we are still in section 4.1 and we are looking over example 8 from your book. So, and again, what is here the vector space? Here, the vector space is an interval from 0 to infinity. So this is all positive numbers, no? Just to make clear, real numbers, no? And obviously, if we just take the regular multiplication, this is not a vector space because, for example, 1 is in here. I multiply 1 by -2, get -2, I drop out. So this is not closed under scalar multiplication. So the point is, the book now turns this set into a vector space. So we need to find a new definition of plus and a new definition of, scalar multiplication. And this time, just because it's getting very confusing, I use a red pen to indicate the new plus and the new times. And most of the time I confuse myself with this, so nevertheless. Okay, so first, if you take two positive numbers, how do we define addition? Okay, this is hard to see, I see. So this is a red plus. Okay, and we add numbers in this vector space, but we have to figure out if it's a vector space by multiplying. So 1 plus, oh no, let's say 2 plus 3 is 6, according to this addition. So if you take now alpha in R and U in V, how do we multiply alpha times U? And again, this is a new multiplication. I make it in red. And then, surprisingly, it turns out you multiply by taking it to the exponent. So, for example, 3 times 2 is 2 to the power 3, which is 8. So this is a new plus and a new times. And we have to check that this actually makes a vector space. The first thing is we check if you multiply two positive numbers, is it positive? Yes. So this is a positive number. So we are in V. And if you take a positive number to any exponent, it's also positive. So that's in V. Remember, if I would multiply a positive number by -2, in the regular sense, it becomes negative. So that is impossible because we have to stay positive. But this, let's say 3 to the power of -2 is 1/9, it's positive. So that works, no? Okay, now we have to check properties. So that means property number 1 is okay, property number 6 is okay. And one more time I go through the other properties, but then that's the last time I do this, and you do a few of them at home. So the next thing is addition is commutative. So we do U, V with the new plus. By definition of the new plus, this is U times V in the regular sense. Now we multiply two real numbers. We can actually commute into V times U. And it turns out this is V and the new plus with U. So that's okay. And again, this is true for every U and V in this vector, in this set, capital V. Number 3, we have to show it's associative. So I take now U, V, and W, so 3 positive numbers. And we have a new plus here and a new plus here. And let's start with parentheses here. It really doesn't matter where I start. Okay, so now we use the definition of this plus, so it becomes u v times w, and this is still the new plus. Now we resolve this plus into u, also again, that's the definition of our new plus, u v w. Now we multiply just 3 real numbers, first v times w, then times u, but multiplication in the real numbers is associative. So it turns out in the real numbers, it really doesn't matter in which order I multiply. So I can also do u times v times w. Okay, now I go backwards. I put in the definition of our plus. So we have u v w, and that's the new plus. And one more time, we use the definition of our new plus and say this is u v w with the new plus operations. Okay, so this was just checking that it works out. And number 4 is the first part where we need to be creative. We need to define a zero vector. So we need to find a positive number. If I add it to any other number, the number will not change according to this definition. So I need to find a positive number such that if I multiply, the number doesn't change. So what is my zero here?
1.
It's 1, because if you multiply by 1, the number doesn't change. So for us, the zero vector is the number 1. 1 is a positive number, so there we just have to check that it does the job. So u plus 0 is, because we know 0 is 1, is u plus 1 according to the definition. So this is actually what we just decided to check. And according to the definition, that is u times 1. But now the real number property, when you multiply anything by 1, it stays. So u plus 0 vector is u for every u. Okay, that works out. Number 5, second time we have to be creative. So we take a number u in the positives, and we need to say, what do we mean by inverse of u? Inverse with respect to addition. So again, we need to find a number, let's say for u, we need to find a number, if you multiply, you get 0. But remember, 0 is 1. So which number can you multiply to get a 1? Like I said, it's a little bit brain twisting. So remember, 0 is 1. Now you need to multiply something to get a 0, which means you need to multiply so you get a 1.
1 over u?
Yeah, 1 over u, the inverse. The multiplicative inverse is here our additive inverse with respect to the new minus. So I should also maybe make this a new minus. So it's a new minus is 1 over u. And that's okay because we're only looking at positive numbers. For positive numbers, I can always do 1 over u. Now we check u plus the new inverse is, now let's use this definition first, is u plus 1 over u. Then comes the definition of plus u times 1 over u, which is 1, and that's our 0 vector. So u plus minus u is 0 for every u. So for every u, we have an inverse negative u, a red inverse. No? Okay, property number 6 is...
Professor?
Yes?
Can you just explain again why we're saying this 0 vector is equal to 1? Is it just to
yes.
make it work, or?
Yes, also, in some sense, yes. You have to find a 0 vector such that if you add this guy, it doesn't change the number, no?
Right.
Okay, now you have to say, what do we mean by adding? Okay, actually we mean multiplying. So you have to find a number that if you multiply with another number, this number will not change.
Okay, so basically, since it's a multiplication, we can't multiply by 0. We have to keep it
You can,
equal to
but
1.
you will not get the same number. If you multiply 2 by 0, it gets 0, no?
Right, right. Okay.
So you have to find a number such that 2 times the number is actually 2, and not just for 2 for every number. No, that's just an example.
Okay, thank you.
Also, I mean, that happens because of the weird things how we define addition, no?
Right.
Yeah, addition is multiplication. The new addition is the old multiplication. So that implies that the new 0 is the old 1. Okay, so number 7 is now we come to the distributive laws. So now first distribution with 2 vectors. So we do alpha, u, and v. So this is now the new addition. And for the first time, we have the new multiplication. I hope you see this is red and this is red. Doesn't really show very clear on my screen here, but okay, I hope, yeah. Okay, so now we do the definition, let's say, of the new plus. This is alpha dot, and we add by multiplying. Then comes the definition of the new times, and that is uv to the power of alpha. Now again, we are back in the real numbers, and if you have a product to a power, you can actually distribute the power. So this is u to the power of alpha times v to the power of alpha. And this is all done here in the real numbers, nothing from the new definition. But now we start going backwards, because you say this is the old multiplication, that is the new plus, no? So this is u to the power of alpha plus v to the power of alpha. Okay, but now exponent, that's our new multiplication. So this is now definition of our new multiplication. This is alpha u alpha v. So here we have the new multiplication, and in between we have the new addition. So alpha distributes. So again, it works. So this is just perfect in some way, how this all works together. Point number 8 is again distribution, but now instead of having 2 vectors, we have 2 numbers and 1 vector. So we have alpha plus beta u, and that's the new multiplication, but this is the old addition in the real numbers, no? Okay, according to the definition of this multiplication, it's u to the power of alpha plus beta. Then that is now a property of the real numbers. If you have u to the power of alpha plus beta, it's the same as u to the power of alpha times u to the power of beta. There was a rule you learned a long time ago in school. If you have the same base, you can add the exponents, no? So that was kind of a rule you heard. Not sure if you ever showed this in your high school or earlier, but okay. So this is the old multiplication. So now we go back to the new definition of plus. This is u to the power of alpha plus u to the power of beta. And now this is according to the definition of our new multiplication, alpha u beta u, where here we have the new multiplication and the new addition. And you see from here to here. That's true for every alpha, beta, and u. So property number 7 is okay. We can distribute over 2 numbers. Property number 9 is if you multiply 2 numbers first and then with the vector, should be the same as first multiplying one number and then the other number. So let's start with this, alpha, beta. This is the old multiplication between numbers. And we multiply with the new multiplication with a vector. So we do definition of our new multiplication. That is u to the power of alpha, beta. Now we have a multiplication in the exponent. That means you can do u to the alpha first and then u to the power and then power beta later. So this means 2 exponents multiply. Again, that's a rule which you hopefully have seen for the real numbers. So this is u to the power of alpha to the power of beta. And sorry, I have to just to come out. It doesn't really matter, but I like to come out in the correct way. So let's do this is beta alpha. Remember, alpha times beta is the same as beta times alpha. Real number multiplication is commutative. Okay, now we use the definition of our new multiplication to bring down the alpha. So this is alpha u beta with the new times. And again, u to the power of beta is the same as beta new multiplication times u. Oh, sorry. Again, I'm wrong. It's alpha first, then beta and u. And here we have the new multiplication. Here we have the new multiplication. And we have parentheses here because that was one identity here. Okay, so again, that works out. Essentially, it means it doesn't matter. We actually don't need the parentheses. Just skip it. It's fine. So that is what this means. But now we see when I say it's just skipping, it's kind of funny. So if we remove this, it really changes the meaning of times. No? So you have to be careful what times you actually use. Okay, and finally, property number 10 is if you multiply a vector by 1 with the new multiplication, it is actually u to the power of 1. And then again, that's a, okay, sorry, that's its definition of times. Then this is properties of the real number. If you take a real number with exponent 1, you just get the real number. This is true for every u. So multiplying by 1 doesn't change the vector. Property number 10 is fine too. So this shows this new addition and multiplication turns the positive numbers into a vector space. The positive numbers by itself with the old multiplication and the new old addition is not a vector space. But with the new addition and multiplication, it becomes a vector space. Okay, so this kind of a little bit shows you, oh, suddenly you have possibilities which you might not even think of. The question is, why is this good? But that's another question. So the point is, it's not always so obvious how you turn a set into a vector space. And that's in general true if you're, let's say, I'm not sure if you're computer science, that's maybe the only time you ever see things like this. But in mathematics, it might happen later on in other classes with certain multiplication and additions. You can turn things into vector spaces. Question is, why would people do this? The reason is for vector spaces, we know a lot. So essentially, keep in mind what I said at the beginning. The definition of a vector space in computer science, the equivalent would be reusability of software. If you have a software which runs like a well-functioning software, you like to use it in different areas. Same thing in mathematics. Vector spaces are studied since 150 years. We know so much about vector spaces, structures of them. So if anything turns out to be a vector space, we have the full machinery available to analyze it. So it's really sometimes a practical thing, turning something into a vector space and suddenly say, oh, that right away means something like this. Or right away, once we have a vector space, we can determine how big it is with something which later on we will learn, which is called dimension. Or we have things like bases, and we can describe things in different bases. So in the moment you have a vector space, you have essentially a toolbox, which you can apply to a vector space. Okay, and then the last thing, as I said, it's just a sequence of properties, which is always good to know. And as I said, I will not go into the proof. The proofs are all kind of fast, not difficult, but they're really playing around with all these definitions. So if you have a V, a vector space, also for us always a real vector space, then if you have a vector U in V and alpha in R, then the following things are true. Whenever you multiply a vector with 0, so this would be whatever your definition is, for example, here this guy, you get 0 vector, no? Which here translates into, if you take any number to the power of 0, it becomes 1, and 1 is 0, no? So part B, if you multiply any number with a 0 vector, you get the 0 vector. Again, in our last example, if you take 1 to any exponent, it always stays 1. Okay. So part number C is, if you multiply a vector by -1, you actually get the negative. That translates here into u to the power of -1 is the same as 1 over u. Okay. Part D, if alpha times u is a 0 vector, we can always argue that alpha must be 0 or u must be the 0 vector. Because if alpha is non-zero and u is non-zero, that cannot happen. And finally, the last thing, E, that's a soothing fact. It's also not clear from the beginning, but it's not so difficult to show. The 0 vector and the inverse vector are unique. Like here, remember, we are looking for what do we use as a 0 vector, and we came up, oh, 1 works. Now the question is, can anyone come up with another number which also works? It turns out this thing tells you no. If you find 1 0, that's it. There's not another 0. Again, you can say, so what's so special about this? Again, in mathematics, we have structures, not vector spaces, other things, where suddenly there can be 2 or 3 zeros, or infinitely many zeros, and they're different. So they act like zeros, but they're not all the same. Here, for a vector space, this kind of more strange thing cannot happen. So that is kind of a good thing, that the inverse of u, also minus, what we call negative u, and the 0 vectors are unique. Once you find one, you have them all. Okay, so this kind of, I hope all of them are not so difficult to remember, because that's how we work anyway, and the uniqueness is an extra add-on. So that's good to know. And so this was kind of our crash course into vector spaces. So vector spaces, whatever acts like Rn, we call vector space. And this example shows you sometimes it can look strange. Okay, after this, we start with section 4.2. Again,